I'm sure you've heard someone saying, or even you yourself believing that what a lot of space enthusiasts are calling for, setting up a permanent human outpost in space, is not practical economically, and we have better uses for our money than to waste them on something like that. After all, one of the biggest channels about macroeconomics, Economic Explained, believed so and made an entire video trying to prove that point. But as a space enthusiast myself who also happens to have a newfound interest in economics, I believe those two can work together, that there are good financial incentives that will motivate people to go and develop space. Unfortunately, all the videos covering this topic that I can find on the internet explain it in a manner that somewhat resembles this meme about the business plan of the underpants gnomes from South Park. They have a plan. Step 1, collects underpants. Step 3, profit. Step 2, who knows? They may or may not state something like if you want these futuristic dreams of yours to come true, or if you want to fully explore space and do all these cool new things, then you need permanent human outposts and infrastructures in space to support that. Or something like, humanity have no future if we don't expand into space. Then they move on to vaguely explain how we can do all of that while producing something of value to make the whole process seem profitable, or at least self-funding, without ever exploring how those products are going to fare with alternatives on the market. Or how are we going to get to that point of profitability? What are the upfront capital expenditures required to get to that point? Are they practical? What's the expected timeline for return on investment? Is it reasonable for investors? Or at the very least acknowledging that most people aren't space enthusiasts, so unless there's some really good profit to be made and the return on investment is clear, most people aren't going to fund or support these ideas at all. That's not to mention that the arguments about the profitability of products produced in space is superficial at best, lacking any sufficient depth or detail enough to persuade anyone other than those who are already interested in space development in the first place. And so I decided to make this video to try to explain what economics incentive will motivate people to go and develop space, how are we going to get to that point of profitability, and how those products are going to fare in our current free market. Let's start with transportation, which generally speaking is the single most important factor when predicting whether something is economically viable or not. As even here on Earth, there's a really strong correlation between countries that are landlocked, which means they don't have access to the cheapest means of transportation available currently, ocean shipping containers, and economics underperformance. This problem is so well documented that the UN even have an entire program dedicated to supporting this country. Historically, the cost of going to space has been pretty high, driven up predominantly by the high R&D cost that goes into building only a few rockets. So essentially, those rockets are like custom designed or limited edition products, and the cost going into building a single-use system. The key here is then to develop a mass-produced, fully and rapidly reusable rocket. The mass-produced part will help to spread out that high R&D cost over many hundreds to thousands of rockets, and to help make it cheaper and easier to build every single one of those rockets. The fully and rapidly reusable part will help to further spread that cost of building a single rocket over dozens to hundreds of launches, massively driving down the cost per launch of that rocket. And with several companies and agencies around the world like SpaceX, Blue Origin, and the China National Space Agency working on this problem right now, it will only be a matter of time before such a system becomes operational. And so the question now is to figure out what will the impact of that be on the cost per kilogram delivered to space. For this, let's look at this analysis done by the people at Payload Research for Starship. Their estimation is that the cost of building a Starship Super Heavy combination initially will be $90 million, dropping to 33 to 50 million once entered mass production. And with the Falcon 9 booster not being designed for reusability from the get-go, and still managed to successfully recover 29 times as of July 2025, I'm fairly certain that Starship will easily be able to pull over 50 or even 100 launches per vehicle built. And that basically means that the cost of building the rockets will essentially be negligible when calculating the final launch cost of the rocket. We also have an estimation for launch cost to be 10 million, with 1 million being fuel costs and 9 million for other operational costs, both of which can drop down further in the future as launch frequency increase. My personal speculation is that as launches increase, especially for newer types of fuel like methanol used for Starship, the fuel production process will get more refined and efficient, and therefore the fuel cost will drop below $1 million, with numbers like $500 or even $250,000 for fuel costs not being unimaginable. As for other operational costs, 90% of the total launch cost seems a bit too high, especially given that space travel is arguably, hands down, the single most automated form of transportation on Earth period. And the rapidly reusable part means that the checkup and refurbishments in between flights will be significantly lower than that of Falcon 9 or the Space Shuttle, approaching that of inspection in between flights for an airplane. And so if we take the cost breakdown of flying an airplane as our reference point, of which 20 to 40% is fuel cost, and then we take the conservative estimation that fuel cost for rocket launches will be on the lower end of that range, so 20%, because rockets need more inspection and refurbishments in between flights than airplane, then all the operational costs should only be 4 times as much as fuel cost, resulting in a number between $2 and $3 million. And so combining those two, a reasonable estimation for launch costs in the long term for launch system of this class will be around $2 to $4 million. Given that Block 3 of Starship is expected to be capable of carrying 300 tons to low Earth orbit and 200 tons to higher orbits, the cost per kilogram delivered to space will then be $7 to $13 per kilogram to low Earth orbit and $10 to $20 per kilogram to higher orbits. Not extremely cheap, but cheap enough to be comparable with you sending a package using post-delivery. This kind of drop in launch cost is also supported by the general downward trends observed in the past few decades as rockets that are built in larger numbers and partially reusable rockets enter the market, which makes them not just merely optimistic technological speculation, but is also supported by extrapolation from past data. There are also other proposed mechanisms to deliver payload, especially raw materials, to space that can even be cheaper, like spin launch developed by the company with the same name, and mass driver, which is a giant coil gun, both of which aim to throw the payload directly into orbit at very high velocity without the need for traditional rocket fuel, which can be extremely useful and will be discussed for the later stages of space development. But for now, the only thing on the horizon in the near future is mass-produced fully and rapidly reusable launch vehicle, and so that will be what I'll be mostly talking about in this video today. Now, to be absolutely clear, $7 to $13 per kilogram to orbit is still significantly pricier than ocean shipping container, which for mass shipment can deliver a kilogram of product for a fraction of a dollar. And so there's no economic incentive for anyone to go and get anything from space that already have comparable alternatives here on Earth. Therefore, the first few industries that are established in space will have to simultaneously have products that are cost-dense enough to be able to absorb that higher cost of launching to and from space without significantly increasing the final price of the products, have clear comparative advantages as compared to getting those same products from here on Earth, and have low infrastructure required to get significant volume of production, to lower the barrier of entry, quicken the return on investment, and lower the risk for investor. With that, only space tourism and in-space manufacturing will fit all of those criteria simultaneously. Space tourism is quite self-explanatory, and hopefully I don't need to explain to you why there will be an awful lot of people who will be interested in purchasing a ticket to go to space if the price of such service drops to $5,000 to $10,000 per person. The only infrastructures that will be needed when starting out are only a fully and rapidly reusable launching vehicles, which is, as discussed earlier, is already in development, and life support system for that vehicle, which is already in development for NASA's HLS program, and I believe the Chinese have something similar on their part as well. With those two, you can already carry out missions like the Polaris Dawn mission, which just happened last year, and is the world's first privately carried out spacewalk. Then you can gradually build permanent infrastructures in space to support your industry as demand increases. In all likelihood, space tourism will be the first industry to be established in space, and will pave the way for other industries that will come after it. As for microgravity manufacturing, the unique condition of space enables things that weren't possible before. Things like printing entire human organs out of stem cells, which has been in development with 3D bioprinting technology for the past several decades, but has never succeeded due to the need for scaffolding structures to support the cells and keep them in place under the influence of gravity, which both interacted badly with the tissues being grown and limited the tidal structures that can be created. Early demonstrations for the viability of this technology has been tested in the biofabrication facility on board the International Space Station. And given that over a dozen people die every single day waiting for suitable organs to be donated in the US alone, and donated organs still have a high chance of getting rejected by the body after 10 to 15 years, there's reasonable ground to believe that the needs for readily available and fully genetically compatible organs that won't get rejected by the body and won't need constant reliance on immunosuppressants will be extremely high, with potential costs running in the tens to hundreds of thousands or even millions of dollars per organ that weighs only a few kilograms. Similar to growing human organs, growing protein crystals in space is also better than growing it here on Earth. The unique conditions of space allow for higher quality and even entirely new crystal structures to be grown. The benefits of growing protein crystals in space was first observed during the age of the Space Shuttle program, and is currently being explored by several startups and pharmaceutical manufacturers, including Bristol Myers Squibb and Merck & Company. Protein is one of the four main biomolecules in living beings, but framing it that way is undermining just how important it is to the pharmaceutical industry. Out of the four, nucleic acid is for information encoding, carbohydrates is burned for energy, phospholipids is mainly used to form membranes for cells and organelles. So that leaves protein to do most of the heavy lifting functions that enable life, from transporting other molecules around, serving as enzymes and catalysts for other reactions, to forming antigens, antibodies, and hormones that regulate different functions in the body of complex organisms. And for that reason, it's also usually the primary active pharmaceutical ingredients of many drugs. That means by being able to grow higher quality protein crystals and new ones that weren't possible before, we'll now be able to better understand the mechanisms of many diseases to develop new treatments, develop new and more effective drugs, and drugs that are more resilient to a wider range of environments, or easier to use. And given that pharmaceutical products are, generally speaking, like human organs, are very cost-dense, with small bottles of many types of drugs running in the hundreds to thousands of dollars while weighing less than a kilogram, and most of which the active ingredient only makes up a tiny % of the final product. This can also be a viable candidate with high enough profit margin to be able to offset the higher cost of working in space. Those are the two best examples to illustrate my point, but there are also other products that are made possible by the unique conditions of space that will be of immense economical value here on Earth, given that we can get launch costs to be low enough. Those things are, for example, the Z-Plan fiber optic cable, which will eliminate the needs for costly undersea repeaters every 6 to 70 kilometers for transoceanic internet optical fiber, while also increase the security for the cable as weak points for cyber threats to breach are eliminated. But not only that, these products that are currently being explored for in-space manufacturing have high profits of margin to absorb the higher costs of launching to and from space, and is exclusively possible in the environment of space, but also products that have low infrastructure requirements to achieve commercial production volume, by which I mean that they don't require a huge complex production line established in space to achieve mass production, which will be costly, technologically challenging because we've never done something like that before, and inevitably increase the risk of the endeavor, discouraging the investments needed to get them started in the first place. Instead, the production process for these products are usually small, simple, and self-contained. Take the 3D bioprinting organ process for example. The only things that you need are the stem cells that you're going to print the organs out of, the 3D printer that's used to print the organ, the bioreactor that's used to house the previous two and the organs being printed, and some kind of storage facility to preserve the organs before transporting them back to Earth. All of that can comfortably fit inside a refurbished starship, if not several of them in one. And with one launch, you can print dozens to hundreds or even thousands of organs before transporting them back to Earth for use. With one organ costing in the tens to hundreds of thousands or even millions of dollars, you will still have a very profitable business, even if you can only print a few dozens organs per launch. Or for the protein crystal manufacturing process in the pharmaceutical industry. From the sounding of it, I guess that you might be thinking that this will require machineries like those seen in processor manufacturing plants. But in reality, it's much more simple than that, and it's more akin to your average chemistry lab. So equipment for mixing, heating, cooling, and evaporating fluids. And to show you how simple that is, there are companies like Royal Space Industry that have planned to fit all of that into a capsule, smaller than the average size of a sedan. Combining that with the fact that we'll only be manufacturing the active ingredients of the drugs, which makes up only a tiny fraction of the final drugs, we'll be able to manufacture a very sizable volume of medicine before we have to have permanent infrastructures in space. And to give you an idea of how much medicine we can manufacture this way, the entire US consumption of Pfizer COVID vaccine in 2021 and 2022 combined, a few hundred million doses, the crystalline mRNA in all of them is only less than 2 gallons. So less than 2 of your average milk jugs. Therefore, these early day in space manufacturing industries can start out with a very profitable economic model by carrying all the equipment and material needed up and down with each launches. And as demands increase, which they certainly will given the market size of these industries, they can move their production line permanently onto the next generation of private space stations, which will come online sometime in the 2030s, with a lot more space and more advanced equipment than the current ISS. Or they can just build their own space station using the profit they made from selling the early day products. And once that happens, we can then expand the manufacturing industry to make products that require more infrastructures to get started, like making Z-plan fiber optic cable or semiconductor substrates made from new materials. Because now we have the foundation laid out by earlier industries for us, so the risk for investor is significantly lower. This model, where the products being produced are ones that are exclusive to space, have high profit margin to be able to absorb the higher cost of flying to and from space, have low infrastructure requirements when starting out, and have quick return on investment, meaning it will be the one that will get the most funding from the investor, and will most likely be the first step for our process of developing space. That is in stark contrast to the future that many space enthusiasts are proposing, trying to build all the infrastructures first, and then try to make products that the markets aren't really ready for. The profit margin is questionable depending on the products and is hard to be seen in the current market condition, have high capital expenditure requirements when starting out to build all the production lines and stuff, and having to potentially sustain that funding for decades before any profit is made. Meaning that in the eye of a cold, heartless economist, or even the average person, it's just a really bad investment. I mentioned all of that not to try to kill anyone's dream of a spacefaring civilization. After all, it is in our DNA that we all hope one day our grandchildren will be able to traverse the star and explore places that we can only imagine right now. But to bring a more realistic expectation for what our future might look like. As mentioned in my previous video about climate change, economics is not just for profit, but it's a tool to help us decide out of all the needs and wants of over 8 billion people living here on Earth, which one deserves prioritization and which one doesn't. And so as disappointing as it may sound, if we want anything to be developed in space, we'll need to make every single step leading up to that final goal economically profitable, if we don't want our efforts to end up like the Apollo program where we go somewhere once and never come back. Because if I remember correctly, the last time that we did something that wasn't economically profitable, the Apollo program got shut down and we got stuck in low Earth orbits for over 5 decades. We should also not get ourselves caught up with unrealistic plans and expectations as well, as that's a recipe for forming a market bubble. And when something like that bursts, Not only will it significantly slow down progress in the field, but will also cause the loss of trust from both investors and the public, which will make it significantly harder for us when we need to call for support for future projects. Now, with all of that out of the way, I presented to you my arguments for how we might develop industries in space according to science and economics. But some of you might be quick to point out that those advantages that got us to set up industries in space in the first place are just general property of space. And if that's the case, why would anyone want to go anywhere beyond Earth orbits? That's a really valid question, and the answer to that has something to do with all the raw materials that we'll have to supply the industries with. The abundance of those materials that can be found on the moon, and the gigantic gravitational well that's created by planet Earth. All of that is the topic for my next video, the economic incentives for deep space development. Until then, thank you for watching. My name is Tai Yung, and this is I Have a Dream. So, another guy watched my video and gave me some reviews. And given that my next video heavily relies on the assumption that there will be a large and robust in-space manufacturing industry in a few decades, he was skeptical about the market size for these industries, whether they will be as large as I imagined them to be. And he raised some doubts about the competitiveness of products that require extensive infrastructure to be established before any production can begin. So, if you have those same questions as him, stick around and I'll try to answer them now. Let's start with organ printing. Globally, there are a few million people who are in desperate need of organ transplants right now. The vast majority of them either need kidneys or livers. Kidneys weigh a few hundred grams a pair, whereas livers weigh 1.3 to 1.5 kilograms each. So globally, we currently need at least a few thousand tons of organs. That's not to mention that if you watch my third video of this series, you'll know that there will be a lot more demands for these organs once the technology is proven viable. Obviously, we're not gonna print organs out of moon materials, so what will be of our interest here is the materials that will be needed to build the infrastructures to print these organs, which will be at least an order of magnitude higher than the organs themselves. So at least a few tens of thousands of tons. If you need something to compare that to, a single cargo ship passing through the Panama canals can have a maximum weight of both the ship and the cargo to be 50,000 tons. So the infrastructures will be equivalent to roughly one of those cargo ships. Next, we have the pharmaceutical industry, which annually produces in the tens to hundreds of thousands of tons of medicine. Again, we're not gonna synthesize medicines out of moon materials. So what will be of our interest here are the infrastructures that support the industry, which will be at least in the hundreds of thousands to millions of tons of materials. If you need something else to compare that to other than the cargo ship that I mentioned earlier, then we have the Burj Khalifa, the tallest building on Earth, which weighs a total of 500,000 tons. So roughly 10 of those cargo ships. Next, we have the Z-Plan fiber optic cable, which will be used exclusively undersea. So we can ignore all the terrestrial applications for those fiber optic cable. Undersea fiber optic cables total 1.5 million kilometers, which weighs roughly in the tens of thousands of tons. This one, we can start to synthesize them out of moon material, at least partially. Also, the infrastructures will be at least in the hundreds of thousands of tons. So, quite a sizable industry. Next, we have the semiconductor industry, which was also where I get that quote of the cost of building infrastructures in space will be 10 times higher, and there's no way that the performance can match that. Which I totally don't agree with the statement that it cannot be 10 times as efficient as here on Earth. But that will be a topic for another time. Here I'll solely talk about the 10 times higher cost of building infrastructures in space. The cost of building a modern chip fabrication plant is $30 billion. With just $1 more billion, So a few percent of the total cost of building one of those plants, you can already transport 100,000 tons of materials to space. So contrary to popular beliefs, the cost of transportation will not be the significant factor that will cause the increase in cost of building infrastructures in space. What we will also not have to worry about are any form of life support systems on board, because 98% of the ship fabrication facility is automated. The last 2% are teleoperated. So there will be no life to support and any form of R&D costs. The industries that come before this, we have already figured out how to build infrastructures in space. There's no need for us to reinvent the wheels here. What we still need to worry about are radiation shieldings to protect the delicate machineries inside, and extra strengthening for the structure to survive launching to space, both of which will not be present for plants built here on Earth. But those extra costs can be offset by the extra cost of having to maintain a very clean environment here on Earth, having to strengthen the structure not to survive launching to space, but to support all the heavy machineries that are used in the plants themselves, and the cost of the piece of real estate that the whole facility is built on. So all in all, the cost of building infrastructures in space can be more expensive than building them here on Earth, but nowhere near 10 times more costly than building them here on Earth. As for the market size of this industry, I really don't think it needs any extra explanation from me. Every single thing that runs on electricity around you have at least some semiconductor in it. From your smartphone, laptop, desktop, to solar panels, cameras, LEDs, to even your phone chargers use semiconductor in them. So the market size for this is really out of the question. Finally, we have super alloys. This is not your average metals in your cast iron pans in your kitchen, but highly specialized, specifically engineered alloys that can withstand extreme conditions. It is used extensively in the aerospace industry, the energy sector, various industrial processes, and high-performance vehicles. The global production for this industry is in the tens to hundreds of thousands of tons. So the infrastructures will be at least in the hundreds of thousands to millions of tons. This is the first industry where potentially all the products and the infrastructures can be made out of moon material exclusively. So this will be of huge importance to the development of a moon industry. It's also here that I want to address one final fallacy when people talk about the competitiveness of the products on the market. A product does not need to have an increase in performance that match or exceed the increase in price. There's no way that the increase in performance for an airplane by using super alloys over normal alloys can match the 10 times increase in cost of the materials. And yet, because the vast majority of the cost of flying an airplane, as discussed earlier, is the fuel cost, not the cost of the airplane themselves. It made it worthwhile for airliners to pay 10 times more for the super alloys over the normal alloys for the extra fuel saving. So the moral of the story is that you don't need an equal or even higher improve in performance as compared to the increase in cost of the thing, so long as the improve in performance save enough on something else. And with that, I hope I've cleared out any remaining doubts in you. Thank you very much. See you in my next video. Bye bye.